Now we continue with the next one. Now we get the relation between sequence voltage components of R phase using one of the boundary conditions. So now we mention the sequence voltage components of R phase. So first we may write for this, what about Vy per unit? Same as Vb per unit. What is Vy? Vy0 plus Y1 plus Y2. What about Vb? B0, B1, B2. Now mention symmetrical components in terms of R phase. So how to represent now? Y0 is a VR0, K square VR1, K VR2. What about right hand side? VR0, K VR1, K square VR2. So VR1 on either side gets cancelled. If you take out VR1 common, you get K square minus K. There you take K square minus K, VR2 per unit. So these two gets cancelled. So what is VR1 per unit equal to VR2 per unit? So this is the sequence voltage components of R phase. Now we find out what is the positive sequence current in terms of sequence generated EMF. So now we have to find out the positive sequence current in terms of positive sequence generated voltage, that is ER1 per unit. So for that you make use of the relation VR1 per unit is VR2 per unit. What is VR1? You write it as ER1 minus J IR1 X1 equivalent. What is VR2? Minus J IR2 X2 equivalent per unit. And you know that IR2 same as minus IR2 same as IR1. So simplify this one and find what is IR1 per unit. How much it is? ER1 by J X1 equivalent plus X2 equivalent. So this IR1 per unit here. So positive sequence current in terms of positive sequence generated voltage ER1 per unit. Now we find out what is the per unit fault current, IF per unit. How to find what is IF per unit? Same as IY. It is same as how much? IY. And how you mention IY? Fault means system becomes unbalanced. How to represent an unbalanced system? Using symmetrical components. Further you write in terms of R phase. So I R naught, here K square IR1, and here K IR2. So we have IR naught per unit, IR2 we write minus IR1, and how much IR naught per unit is for line to line fault? 0. So we write only K square minus K IR1 per unit. And what is the value of K square minus K? You get minus J root 3. You show the magnitude here. It is root 3. IR1 how much? Substitute here. ER1 by J x1 equivalent plus x2 equivalent. This is how you write what is the per unit fault current. So this is how you calculate the per unit fault current. Now once you know the fault current in per unit, it is simple to express that fault current in amperes. It is simple to express the fault current in amperes. Similar to LG fault we can mention. So fault current in amperes. So how to write this one? IF in amperes is IF per unit into the base current in amperes. What about base current now? It is base volt ampere divided by root 3 times base voltage base current. Root 3 times base voltage base current. Now we have to find subtransient reactance in per units. The per unit subtransient reactance XD double dash per unit. What is the definition of subtransient reactance? The reactance offered by alternator immediately after occurrence of fault. You can check the denominator. What is the total reactance? X1 equivalent plus X2 equivalent. This is the subtransient reactance. Now how you draw the sequence networks now? Zero sequence current IR naught is 0. So no need to draw the zero sequence networks. Only you draw positive sequence network and negative sequence networks. So how to draw them? You know this, IR1 equal to minus IR2. And total reactance is the sum. So what you call this type of connection as? Currents IR1 per unit equal to minus IR2 per unit. Reactance is sum. So you say that positive sequence network and negative sequence networks are connected in anti-parallel. So we say that positive negative sequence networks are connected in anti-parallel. So we connect them now. First positive sequence, then you represent negative sequence. So for positive sequence, X1 equivalent per unit, ER1 per unit. How much current? IR1 per unit, source terminal voltage VR1 per unit. What about this one now? The reactance X2 equivalent per unit. How much current? IR2 per unit. What is terminal voltage? VR2 per unit. You can observe IR1 per unit equal to minus IR2 per unit, and the total reactance is the sum here. This will name it as anti-parallel connection. Now we check the next one, the per unit neutral current. First we deal with the case 1, balanced condition. So IN is equal to IR plus IY plus IB 0. Now the case 2, unbalanced conditions. So how much IN per unit is? 3 times IR naught per unit. Here IR naught per unit is 0, so IN per unit is 0. Now we check the next one, the per unit voltage to neutral. So VN per unit. Where you deal with the case 1, balanced conditions. So what is VN per unit formula? IN per unit into XN per unit. As IN is 0, VN is also 0. Now the case 2 is unbalanced conditions. So VN per unit formula is IN into XN per unit. IN 0, so again VN is 0. This per unit voltage to neutral. Next we represent short circuit current in amperes. Pressure is same like the last fault. XD double dash per unit is XD double dash in ohms IB by VB. Now get that to denominator, VB by XD double dash in ohms. What is VB by XD double dash in ohms? Short circuit current in amperes. So from this, how to write the short circuit current in amperes? It is the base current in amperes by XD double dash per unit. Same formula, but only XD double dash changes, and it depends on the type of fault. Formula is the same, only the value of XD double dash changes here. So, how to write the short circuit MVA now? It is the base MVA divided by XD double dash per unit. Base MVA divided by XD double dash per unit. Now we have to check, considering reactance neutral and reactance fault, how to represent XD double dash per unit. Considering reactance neutral and reactance fault, what about XD double dash per unit? This is our last point to evaluate. Considering reactance neutral and reactance fault. First you write the formula of XD double dash per unit. What is it? X1 equivalent plus X2 equivalent. Now IR naught per unit, how much for LL fault? IR naught per unit is 0. So observe, if IR naught per unit is 0, then is there any significance for ground to neutral connection? No significance. So whatever may be the ground to neutral connection, or whatever may be the reactance from ground to neutral, as IR naught per unit is 0, there is no significance on XD double dash per unit. So here for LL fault, IR naught per unit is 0. So what we say? There is no significance of ground to neutral connection. There is no significance of ground to neutral connection. So whether it is Xn or 3Xn or infinite, it is not reflected in XD double dash per unit. And now you have the reactance fault. So what is that fault reactance? XF per unit. So you represent that XF per unit as a third term in XD double dash per unit expression. You represent XF per unit as the additional term in the expression of XD double dash per unit. Now two important points please. First we discussed the LG fault. For faults involved with ground, what we have added? We have added 3Xn per unit and 3XF per unit, where in the expression of X0 equivalent per unit. In the expression of X0 equivalent per unit. Now LL fault, faults not involved with ground. So no significance for X0, no significance for Xn, and add XF per unit as additional term in the expression of XD double dash per unit. So I make it clear here, for faults involved with grounds, so what you will do? Add 3Xn and add 3XF per unit, where in X0 equivalent per unit. For faults not involved with ground, so what is the logic? You add only XF per unit in the expression of XD double dash per unit. So this is regarding the 14 aspects of line-to-line fault. So once again practice all these 14 aspects of line-to-line fault. And once you are thorough with all these 14 aspects, any question on line-to-line fault is very simple to evaluate. So please practice all these 14 aspects of line-to-line fault. And now we discuss the next type of fault, that is LLG fault. LLG fault. So include the fault with Y phase and B phase as it is. But further, you say fault is involved with ground here. So IF per unit not equal to 0. Here you represent IF per unit. What about this one during fault? IB per unit not equal to 0. And what will be this IF now? Sum of IY and IB. How much this IF is? Sum of IY and IB. So IF per unit is IB plus IY. So this is how you represent the schematic diagram for double line to ground fault. So IF per unit is flowing to the ground point and IF per unit is IY plus IB here. So apply KCL at this point. How much this IF is? Sum of IY and IB here. And we consider no load condition, solid neutral and a solid fault. This is the schematic diagram. Now we check the boundary conditions. So how many boundary conditions we represent? Equal to number of sequence networks. How many sequence networks? 3. So number of boundary conditions equal to 3. Now first to check R phase. Before fault, during fault, IR per unit is 0. And check Y phase. What is IF? IY plus IB. Now third boundary condition, the voltage relation. Now check here Y phase. And here it is B phase. Now you please observe this point. Y phase here. On either side of Y phase, what you are having? Ground point. Y phase, ground point. So between two equal potential points, do the current flow? Current cannot flow between two equal potential points. Current cannot flow between two equal potential points. Therefore, IY per unit, VY per unit is 0. If there is no current flow through Y phase, because Y phase is between two equal potential points, current cannot flow between two equal potential points. So what will be VY per unit? 0. So what about that VY per unit? It is 0. Similarly, you check B phase. What we have on either side of the B phase? We have ground point. here also ground point. So between two equal potential points, current do not flow. So what is the voltage in the B phase? 0. So what is the voltage in the B phase? It is 0. So these are the boundary conditions. Now we find what are the sequence voltage components of R phase. In LG fault you got sequence current components of R phase. Now we find sequence voltage components of R phase. You make use of the boundary conditions and accordingly you can identify what can be determined. So first we find out the sequence voltage components of R phase. First we find VR naught per unit, that is VR plus VY plus VB. How much VY? Both are zeros. On simplifying, how much you get? By 3 per unit. What about V1 per unit? 3 times VR plus KVY square VB. VY, VB both are zeros. So find how much you get? By 3. Now you find what is VR2 per unit. How much? 1 by 3 times VR plus K square VY plus K VB. VY is 0, VB also 0. How much you get now? VR by 3 per unit. So this is how you find the sequence voltage components of R phase. You can observe that all the 3 components of voltages are equal. So what we mention? VR0, VR1, VR2 equal to VR by 3 per unit. So this is the sequence voltage components of R phase here. Now we check how to express negative sequence current in terms of positive sequence current and zero sequence current in terms of positive sequence current. So next aspect is negative and zero sequence current components in terms of positive sequence current component. So how to analyze this one? Negative and zero expressed in terms of positive. Use this relation. VR2 per unit is VR1 per unit. How much VR2? Minus J IR2 X2 equivalent per unit. VR1 is ER1 minus J IR1 X1 equivalent per unit. So from this you find what is IR2 per unit. Minus of ER1 minus J IR1 X1 equivalent whole divided by JX2 equivalent here. So express negative sequence current component in terms of positive sequence current component. So what about next? Equate VR0 with VR1. So how much minus J IR0 X0 equivalent is ER1 minus J IR1 X1 equivalent. So how to write ER0 per unit minus ER1 minus J IR1 X1 equivalent by JX0 equivalent per unit. So this is how you relate and find out this answer here. So both in terms of positive sequence current components. And now we will find out the positive sequence current component in terms of positive sequence generated voltage. So next is the positive sequence current component in terms of positive sequence generated voltage. So for that you make use of the boundary conditions. IR per unit 0 can be written as IR0 plus IR1 plus IR2. So what about this IR0? You substitute this relation now. Instead of IR0 minus ER1 minus J IR1 X1 equivalent all divided by JX0 equivalent per unit plus IR1 as it is we write. Now IR2 how much minus ER2 minus J IR2 X2 equivalent divided by JX2 equivalent per unit is 0. So we have to simplify this equation and find out what is IR1 per unit. On simplifying, this is the answer you get. ER1 by J. We have X1 equivalent per unit, to that X2 equivalent and X0 equivalent are connected in parallel. are connected in parallel. So this IR1 per unit here. So this positive sequence current component in terms of positive sequence generated voltage. Now further we can find what is the per unit fault current. Further we find what is the per unit fault current. If you check here, what is the fault current? IY plus IB. As fault occurs, system becomes unbalanced. How to analyze an unbalanced system? Using symmetrical components. Using symmetrical components. IB0 plus IB1 plus IB2. So Y0 and B0 you write it as 2IR0. IY1 how to write? K square IR1. IB1 K times IR1. Similarly, IY2 K times IR2. IB2 K square times IR2. So on simplifying this one, how much you get now? K plus K square IR1 plus IR2. How much IR1 plus IR2 is? IR is 0. So IR1 plus IR2 how much? Minus IR0. And K plus K square is minus 1. So minus minus will become plus. We write it as 3IR0 per unit. So what is the per unit fault current? We mention as 3IR0 per unit. Now once you know this fault current in per unit, now you can find what is the fault current in amperes. So fault current in amperes, how you write? Fault current in per unit multiplied with the base current in amperes. So what is the base current in amperes now? It is the base volt amperes by root 3 times base voltage. Root 3 times base voltage. This is the fault current in amperes. Now we find out what is the per unit subtransient reactance. XD double dash per unit. Observe the equation now. You know the definition of XD double dash per unit. The reactance offered by alternator immediately after occurrence of fault. So though we are not able to get denominator here in fault current equation, we have the denominator as reactance in IR1 per unit expression. So that is XD double dash per unit. How much now? X1 equivalent plus X2 equivalent parallel with X0 equivalent. This is the per unit subtransient reactance. Now knowing this subtransient reactance, now we have to draw the sequence networks. How to draw the sequence networks now? In parallel you connect negative sequence network and zero sequence network, and to that parallel combination add positive sequence network. So positive sequence network is connected in series with parallel combination of negative sequence network and zero sequence network. So what we mention here, positive sequence network is connected in series with parallel combination of negative and zero sequence networks. So first to represent the negative and zero, now these two are connected in parallel. So we have negative x2 equivalent per unit, here x0 equivalent per unit. So both are connected in parallel. So you can indicate their currents also, IR2 per unit, here IR0 per unit. What about this voltage? VR2 per unit. What about this voltage? VR0 per unit. And further, how both are connected now? In series. They are connected in series with positive sequence network. So represent the positive sequence network now. Represent the source. What about the source? ER1 per unit. Here X1 equivalent per unit. Say the current is IR1 per unit. What about the voltage now? It is VR1 per unit. So this is how you draw the sequence networks. Check negative and zero are connected in parallel. To that positive sequence network is connected in series. So negative and zero are connected in parallel. To that positive sequence network is connected in series. Now how to write what is IR2 per unit? Observe, IR1 per unit enters here. We have now two reactances in parallel. How you find current flowing through each of the reactances connected in parallel? We apply current division rule. So, what is the current entering? IR1 per unit. Where IR2 is flowing through X2 equivalent per unit. To that what is in parallel? X0 equivalent is in parallel. So multiply in numerator, add in the denominator. Now if IR1 enters like this, current should flow further like this. But IR2 is flowing in opposite direction. So we assign negative sign. Assign negative sign. Similarly, how to find IR0 per unit? Total current is IR1 per unit. So IR0 per unit is flowing through where? x naught equivalent per unit. To this, what is in parallel? x2 equivalent is in parallel. Multiply numerator, add in the denominator. If IR1 per unit enters, current should flow like this, but IR0 is flowing in opposite direction, so a sign, negative sign. So this one or more representation relating negative sequence current and positive sequence current and zero sequence current and positive sequence current. Next we represent what is the per unit neutral current. First we deal with the case 1, balanced conditions. So what is IN per unit? You know it is IR plus IY plus IB 0. Now we check the case 2, unbalanced conditions. So what is IN per unit? We write 3 IR naught per unit. And what is this 3 IR naught per unit? You can also make it as IF per unit. You can also make it as IF per unit. Next one is the per unit voltage to neutral. Now first is the case 1, balanced conditions. So Vn per unit is In into Xn. In 0, Vn also 0. Now we have case 2, unbalanced conditions. What is Vn per unit? In into Xn. And how much In for unbalanced conditions? 3 times IR naught. Are you right? IR naught into 3Xn. But 3 IR naught is nothing but IF. So you can observe here, physically these two are two separate ground points, but electrically they operate at same potential. Physically these two are two separate ground points, but electrically they operate at same potential. So this is how you represent the electrical connection between the two ground points here. So we continue further after this 5 minutes break. Okay, now we continue further with this line to ground fault. So we have evaluated per unit neutral current and per unit voltage to neutral. Now we have to find out short circuit current in amperes. So how you find the short circuit current in amperes? XD double dash per unit outright, XD double dash in ohms multiplied with base current by base voltage. So we write VB by XD double dash in ohms. So what is XD double dash denominator now? Short circuit current in amperes. The short circuit current in amperes is the base current in amperes by XD double dash per unit. And further, we can represent what is the short circuit MVA. How to write the short circuit MVA? Similarly, base MVA by XD double dash per unit. Now important, now you consider reactance neutral, that is 3xn per unit, and reactance fault. Now, how the subtransient reactance is affected now? First write the formula of subtransient reactance. How much now? X1 equivalent plus parallel combination of X0 and X2 equivalent. Now what is the current flowing from ground to neutral? Current flowing from ground to neutral is zero sequence current. And what is the reactance corresponding to zero sequence current? We write 3xn. And where you represent this 3xn now? As a part of this X0 equivalent per unit. So, by considering the solid neutral, we just write only XR0 per unit. But by considering the reactance neutral, we further add 3xn per unit. And what about this XF now, the fault reactance? We have proved that IF is same as IN. If IF is equal to IN, as you have added 3xn, what you add here? 3xf. Where you add? In X0 equivalent per unit. So you know this, IN per unit same as IF per unit. For IN we have added 3xn per unit. What you add for IF? It is 3xf per unit. So the logic is very simple. For faults involved with ground, add 3xn, add 3xf in X0 equivalent per unit. For faults not involved with ground, add xf per unit in XD double dash expression. In XD double dash expression. Questions? Now, so please once again refer all these 14 aspects of LLG fault, and it is very simple further to analyze this double LG fault. Now we have few questions. First question is by Somdev from West Bengal. How we identify that it is LLG fault? From the diagram. Observe here, fault involved with Y phase, B phase ground, LLG fault. R phase ground, LG fault. Y phase, B phase, LL fault. Next question is by Tanmay. If impedance is placed between the short circuit path, that is between Y phase and B phase, how we analyze fault current? Yeah, that is what you are dealing with the last point. Let it be the reactance or let it be the impedance. Reactance fault, I have written 3XF here. If it is impedance fault, you write 3ZF per unit. And for LL fault, that is faults not involved with ground, you mention only XF or ZF per unit. Next question is by Rachel. In fault condition, short circuit MVA increases than normal MVA. Yeah, definitely. XD double dash by default will be less than 1. So short circuit MVA exceeds base MVA. If any rating is beyond, if any value is beyond the rating, then you confirm that short circuit occurs. Next question is by Tanmay. How can we analyze fault current if neutral is not grounded? If neutral is not grounded, zero sequence current IR0 do not flow. So you don't have X0 equivalent per unit. Like in LL fault or in triple L fault, we can come across such conditions. So if neutral is not grounded, that IR0 per unit 0. So as zero sequence current do not flow. So no need to represent zero sequence network, and you don't have X0 equivalent per unit as one of the terms in XD double dash per unit expression. The last question is by Sanju. In LLG connection, how IR0 and IR2 flow in opposite direction to IR1 mathematically? You please refer the equivalent circuit. IR1 is flowing like this, the sequence network. Now we have IR2 flowing like this, IR0 flowing like this. IR1 enters, but IR2 should flow like this. But you want current in this direction, so S sign, negative sign. I have S sign, negative sign, please refer the last 5 minutes session. And here IR1 per unit enters, flows like this. But you want IR0 in opposite direction, S sign, negative sign. Okay. So we continue further after the break.